All right, we're going to take a look at the intermediate value theorem. And for this theorem, I would like for you to know the conditions of the theorem as well as the conclusion of the theorem. So the hypothesis says if f is continuous on a closed interval from a to b. So I'll give you a chance. You'll need to put an a and a b on your x-axis. So draw an x and y axis and label an A and a B on that x-axis. And then I went ahead and plotted a couple of points. It says that f of A, so I just plotted a point straight up from A, and then I plotted a point straight up from B. And the only condition is that those 2 points can't be horizontal to each other. They cannot have the same y value. So make sure that the 2 points that you put on do not have the same y value. And then go ahead and label those as f of A and f of B. And that would be on the y-axis. Those are y values. Then it says k is any number between f of A and f of B. So I put a k value on. It didn't say that it had to be right in the middle. So I put my k value closer to f of B. You could put it anywhere in between f of A and f of B. All right, if all of those conditions in the hypothesis are met, then the theorem says there is at least one number c in the interval from A to B. So in the interval from A to B means that this c that we're talking about is an x value, and it will be somewhere between the A and the B. There has to be a place, according to the intermediate value theorem, where f of c is equal to the k. So one thing I haven't done yet is I have not drawn my continuous function. So I'm going to do that. Now you can draw anything that you want to as long as it is continuous. So I'll just do this. I could have drawn just a line. I could have drawn something that looked like a parabola. You can draw whatever you want to, so long as you have a function and you have continuity. So this picture satisfies all the conditions. We have an interval from A to B. It's closed. That means we have two filled in dots. The f of A does not equal the f of B. K is in between f of A and f of B. So according to this, there must be an x value, at least one, there might be more than one, where we could see a point that is at the k. So I'm going to take a look. It looks like we have one right here where the y value would be a k. Looks like we have one right here where the y value would be a k. And go straight across right there where the y value would be a k. And so that's three c values. I'm going to call it C1, another one here at C2, and a third one here at C3. So we actually have three places where C1, C2, and C3 are between A and B. So in other words, they are in the interval from A to B. And we have found that f of C1 equals f of C2, which equals f of C3, which equals the k. And this intermediate value theorem it may not seem like that big of a deal, but actually it's what your graphing calculators use to calculate the zero of a function. And I'd like to show you that with this next example. So it says, explain why the function has a zero in the specified interval from 0 to 1. So our 0 and 1 would be the A and the B in the theorem. So we have the 0 is the A and the 1 is the B. And so the first thing that we'll have to do is to make sure that the conditions of the theorem are met. And the first condition is that we have to have continuity. Well, that's a polynomial function. So since f is a polynomial, so f is a polynomial, so we can conclude that f is continuous. On your interval from 0 to 1. So that's one of the conditions that has to be met. Another condition that has to be met is that f of a, which in this case is 0, cannot be equal to f of b. So we need to show that. F of 0, I'll plug in 0. And f of 0 gives me negative 2. And then f of 1, so that would be 1 to the third plus 3 times 1 minus 2. And so that gives me positive 2. So we can conclude that f of 0 does not equal f of 1, and we've met another condition of this theorem. And then finally, still in the conditions, we have to look and see, is there a k value, or what k value are we interested in for this theorem? Well, it's asking us explain why there is a 0 in that specified interval. So the 0, that means that how can we know that x cubed plus 3x minus 2 will equal 0 in the interval between 0 and 1? Well, that's because we found out that f of 0 turned out to be negative 2, and that is less than our value that we're interested in, which is the 0 of the function, and that is less than f of 1, which turned out to be positive 2. So if you remember on your graphing calculators, those of you that have used the TI-83, if you're doing second calc 0, the calculator will make you find something that is on the negatives of the y values, and then it will make you find another point that is in the positives of the y values. Well, essentially what they're doing is this. They're finding something in the negatives, they're finding something in the positives, and if that's the case, then the graph has to cross the x-axis in between where that negative value occurred and the positive value occurred. And so that's actually the use of the intermediate value theorem. The graph must cross the x-axis because you went from a negative to a positive. And that's your conclusion on this. The y values change and I'm just going to abbreviate negative to positive. And that would be an application of the intermediate value theorem. So if we take a look at this graph using Desmos, we have your equation y equals x to the third plus 3x minus 2. And I wanted to show you, so we found that f of 0 turned out to be negative 2, that f of 1 turned out to be positive 2. So the graph had to cross the x-axis somewhere in between the 0 and the 1, since our y values changed from a negative to a positive, because this was the ordered pair positive 1, positive 2. So since our y values changed from a negative to a positive, our 0 that we were interested in was in between those two y values. They were in between the negative 2 and the positive 2. Then somewhere in between the two x's, somewhere between 0 and 1, our graph had to cross that x-axis because we had continuity. And that actually did occur at the 0, if I can get it to show up right there, at 0.5961, which is not directly in the middle of 0 and 1, but certainly in between 0 and 1.